A very warm welcome to the second recitation of CS170. Today's topic is number conversions, hexadecimal, decimal, and binary. So, the purpose of this recitation is to introduce the techniques utilized in converting between hexadecimal, decimal, and binary numbers. We will be going through the following topics, starting with understanding why number conversions are needed, followed by binary to hexadecimal and hexadecimal to binary conversions, then color and hexadecimal notation of it, followed by binary to decimal and decimal to binary conversions, and lastly, we look into hexadecimal to decimal and decimal to hexadecimal conversion. So, understanding how the computer data is represented. In the computer, all the data is captured and represented in a binary system. A binary system is where there are only two bits, that is 0 and 1. Only these two bits are used. For the computer, each 0 or 1 is stored in a bit, and the single bit is not useful to the computer. To be useful to the computer, all these bits are grouped together into bytes. So when we have 8 bits coming together, it forms a byte. And then when these bytes are grouped together, it forms words. So the unique combinations of these words have special meaning to the computer and become the instructions. Now, understanding why we need number conversions exactly. So the human eye can easily misread a lot of long strings of zeros and ones. As such, we often convert from binary numbering system to the hexadecimal system, which is the base 16 system. So it is important to know how to convert between the three numbering systems, and it is an important skill. Now let's look into the number conversion table for binary, hexadecimal, and decimal representation. So here under the decimal column, the numbers 0 to 15 are mentioned. Now for these decimal numbers, the hexadecimal notation has 0 to 9 as numbers, and then it is followed by alphabets, which is A, B, C, D, E, F, and so on. Then for the decimal number 10 onwards, the letters from A are used for denoting it. And for the binary numbers, the combinations of zeros and ones is used. So like for the decimal number 0, the binary is 0000. Moving on to 1, it is 001, and so on and so forth. So now let's play a game which is called binary conversion game. It will help us understand binary numbers better. Uh, you can start by just following the link which is given on the screen. Probably some advertisement may be displayed for a few seconds. You can just skip it. So when you go to the link, click on the classic mode and start the game. So I'll just explain the rules of the game. So there are three empty squares on the lower right corner, and three bits need to be selected from the left hand side by clicking on any one of them and dragging the mouse to select the next two bits beside it. So I'll just go to classic mode, and over here you can see that you have to drag the bits over here to match the numbers. So 7 is represented with 111. So you have to select these three uh, cells. So let's do the game. So the rule is that there are three empty squares over here on the lower right corner, as it can be seen, and three bits need to be selected from the left hand side over here by clicking on any one of them and dragging the mouse to select the next two bits. You have to select three bits from here, and then it should match any of the numbers that are there. If the selection is successful, then one of the decimal numbers on the right will be crossed out. So for suppose let's find the number 0. So 0, if we go back to our table, we can see that 0 is represented with 000. So we can just select 000, and so you can see the number is striked off over here. So that is how it is going to be done. And then you have to keep doing it until until none of the numbers are left, and then it will go on to the next level. So let's do it for all the numbers. You have the next number, which is 7. So 7 is represented by 0, 1, 1, 1. So that is going to be 111, and let's see, 111, and that is 7. So that's striked off. Then let's find the number 2. So binary representation of 2 is 0010. So it is going to be 010, which is 2, and that is striked off. Now let's move on to the next number, which is 6. 6 is represented by 110 over here. So 110 is 6, and we find the number 6 as well. Then the last number is 3. 3 is represented with 011. So let's do that, 011. And the third number, the last number is also selected. And with this, we complete the level and we move on to level 2, where 4 bits have to be selected. So this is a very good game to understand how binary numbers work. So I would urge everyone to like go through it once and just play around with it for some time. Then now let's start with some conversions. So firstly, we'll look into binary to hexadecimal conversion. Here the binary number is first divided into group of 2, where each group has 4 bits. So and so here we have 010 11010. So we will divide it into 2 groups, which will be 0101, which is the first group, and 1010, which is the second group. Now, using the table that was there in the previous slide, we can get the equivalent hexadecimal representation for the binary numbers. So we have the first group, which is 0101. So if we go back to the table, we can see that here 0101 is the hexadecimal is 5. Okay. So we'll have 0101 as 5, and 1010 is equivalent to, here it says 1010, which is equivalent to the hexadecimal representation A. So the answer will be 5A. 5A, which is the hexadecimal representation of the binary number, which is given on the screen. Now moving on, now we have hexadecimal to binary conversion. So in hexadecimal to binary conversion, we will find the equivalent binary representation for each of the components. So first is B. If we go to the table, we can see that B has the binary representation 1011. So B will be written as 1011, and then 8 in the hexadecimal column, which it has the corresponding binary value as 1000. So we will basically club these two values. So the binary representation for B8 is going to be 10111000. So this is how binary to hexadecimal and hexadecimal to binary conversions will take place. Now, so hexadecimal notations can also be used to denote colors. We can understand this better by going to this website, the link that I've given over here. If you go to the website, you can see a lot of colors, and when you hover over a color, it will show the corresponding hex value. So this is the hexadecimal code for these colors. Let's check it out for white. So if I hover over white, it says that the hex code is pound and FFFFFF, which is 6 times F. That is for the color white. Now let's hover around black. If we see for black, the hex code is pound 000000. Similarly, you can hover over any of these colors and you can find the hex values correspondingly. I would like ask everyone to go through this website by clicking on the link and explore how the hexadecimal notations are for these different colors. This would be a great way to understand the notation. Then moving on, we have the binary to decimal and decimal to binary conversion. So the steps for conversion is that you have to multiply each component of the binary number by its base raised to its corresponding power. So like for example, over here we have the binary number 0100000001. So here the base is going to be 2, and we are going to multiply each component of this binary number, that is each bit in this number, with the base raised to the corresponding power. So what I mean by corresponding power is when you see this binary number, the rightmost bit will have a power of 0, then the one next to it will have a power of 1, then the next to it will have power of 2, then 3, 4, and so on. So we will take this bit 1, and then the rightmost bit 1, and then we'll multiply it with the base raised to the power 0. Then we will add it with the next component, which is 0 multiplied by 2 raised to 1, so on and so forth. So when this entire thing is done, the calculation gives us that the decimal representation of the following binary number is 65. So again, just to reiterate that every bit of the binary number will be multiplied with the base raised to the corresponding power, and then all of that will be summed to get the decimal representation. And when we talk about decimal to binary, the decimal number is divided by 2 until we get a result which cannot be further divided by 2. Like here, 72 divided by 2 gives remainder 0. Then 36 divided by 2 gives a remainder 0. Then so on and so forth. In the end, we get 1 divided by 2, which is 0, and the remainder is 1. So we have to stop at this place because 0 cannot be further divided. So here is where we stop, and then the resulting binary number is written in the following way. The remainders are read from bottom to the top. They are read from bottom to the top, and they're written from left to right. So if you can see, let's read the binary. Let's read the remainders from bottom to top, which is 1001 000. So this is how it will be written also. So for the decimal number 72, the binary representation is going to be 1001 000. This is how decimal to binary conversion is done. Then hexadecimal to decimal conversion. In this, so hexadecimal is used as a shorthand notation. So it is important that first the hexadecimal symbols are converted to binary, and then from binary the decimal conversion will happen. So to first convert decimal, so to first convert the hexadecimal symbols into binary, the table will be used. So A over here, A has a A has the binary representation 1010 and 9 as 1001. So A9 can be written as this 10101001. Now this binary number will be converted into decimal. And how is it going to be done? As discussed earlier, every bit of the binary number is going to be multiplied with the base raised to the corresponding power, and then all those components will be added to get the final result. So here we have 1 as the rightmost bit with the power 0, then followed by the second last rightmost bit, which is 0, which is raised to the power 1, and so on and so forth, which gives us the answer 169. So that is how decimal to hexadecimal is going to be converted. Then moving to decimal to hexadecimal, the so the conversion that we're trying to do is of a decimal number 680 to hexadecimal. The first thing to do is we have to determine how many hexadecimal digits will be needed. So this will be done by determining which power of 16 produces the largest number that is still less than 680. So if we do 16 raised to 0, it gives us 1. 16 raised to 1 gives 16. 16 raised to the power 2 gives 256. And 16 raised to the power 3 gives 4096. So now 4096 exceeds 680. So we can't choose that. We'll have to choose 16 raised to the power 2. So the number of hexadecimal digits that will be needed is going to be 3, because it's power of 0, power of 1, and power of 2. So they're like, we need 3 decimal digits for that. So now we will divide 680 by 16, and we will keep dividing it until the division can further no longer happen. So when we divide 680 by 16, we will note the remainders. And over here, if we can see that 680 divided by 16 gives a remainder 8, then it goes on to give a remainder 10. Now 10 in hexadecimal is written as A. So that's how it is mentioned there. And then the next division we do, we get the remainder 2. Now we can't do the division further because 0 cannot be divided further. Then the answer is written in the same way as we wrote it for the previous one. The remainders are read from the bottom to the top and written from left to right. So the answer is going to be 2A8. So that is how decimal to hexadecimal conversion will happen. So, I mean, there were a lot of conversions and a lot of concepts together. So we could just do a quick recap and go through all the methods of conversion. So remember this table: hexadecimal, decimal, and binary. Then, so first comes binary to hexadecimal. In binary to hexadecimal, we just divide the bits into group of 4 and then write the equivalent hexadecimal value. Then for hexadecimal to binary, we are going to find the equivalent binary number for each component of the hexadecimal number. That's how you do for hexadecimal and binary. Then we have binary to decimal. For binary to decimal, we will multiply each component of the binary number with the base raised to the corresponding power. And while doing decimal to binary, we are going to divide the decimal number by 2 until and unless like the division cannot further happen. And very important to note that the remainders will be read from the bottom to the top and will be written from left to right. Then going to hexadecimal to decimal, here we will have to first convert the hexadecimal number into a binary number, and then the binary number is converted to the decimal number. So the hexadecimal number is converted to binary number by writing the corresponding binary values for each component. And once we get the binary number, we are going to multiply each bit of the number with the base raised to the corresponding power. And then decimal to hexadecimal, first we will find out how many hexadecimal digits will be needed. And for that, we'll have to produce the power of 16 and make sure that the largest power is less than what the question asks for us to convert. Then you divide the decimal number with 16 until and unless the division can no longer happen. And again, very important to note that the remainders are read from the bottom to the top and written from left to right. So this is all about the different conversions. Now, since we have done so many concepts, it is important to understand, it is important to know that if we understood the concepts well. So I've shared a Google form where there are a few easy questions that you all can just answer, and make sure that you answer all the questions and submit it, because this is how I will be tracking the attendance also. So yeah, and I think that's it for today's recitation. Thank you very much, and have a good day.